Okay, so the next thing we're going to do is we're going to talk about the wave equation. Oops. So one of the things you learned from Physics 1B, and if you haven't taken it yet, you'll take it, is that there is something we call a wave equation, and the form that it has is it's specifically going to be a traveling wave, okay? And it looks something like this. It's a differential equation. Partial differential equation, I guess. Okay. What does this equation say? It says if I have some function y that's a function of x and t, then it will be a traveling wave as long as it satisfies this equation right here. That when you take the second derivative with respect to x and you take the second derivative with respect to time, that they're equal to each other, except that there's this proportionality constant that shows up here, where the symbol v represents the speed of the wave. So our goal with Maxwell's equations is to prove that they produce the exact same equation, except the y's are going to be the electric and magnetic fields. Okay? All right. So any function, how would I want to write this? So let's see, any function y of x and t that takes this form let's write it as a function. Any function that has the form f of x and t is equal to some function, any function of x minus vt will satisfy that wave equation. And it's relatively easy to prove that this is true. I guess the best way to write this would be on the left-hand side to put the y there. So any function y of x and t that has this form, okay, will satisfy that equation. And we're going to look at an example of this so we can understand why this is true, okay, and why such a thing describes a traveling wave. But I'll leave it to you to prove for yourself that this is true, that any function that has this form will satisfy that equation. I'm trying to write way too fast right now. Any function. Try for yourself. Just think of any function you can that has the form of x minus vt in there. It could be x minus vt squared. It could be the sine of x minus vt. It could be e to the negative x minus vt. Any function that has that form will automatically satisfy this equation. This is very easy to prove by just thinking about what these equations represent here. Okay. As an example of such a function, you could have, for example, y of x and t could be equal to something like 1 over x minus vt squared. And as a specific example of this, we could say let velocity be equal to 3. Okay? So then our equation would become y of x and t would be equal to 1 divided by x minus 3t squared. Whole squared, like that. See, it has to be, this whole function, right, has to be the function, right? It has to be, when I say function of x minus vt, x minus 3t whole squared is a function of x and t, right? All right. So what does that look like if we plot it? Well, I did this during the break. Some of you might have been watching me do this. I don't know. But if I want to plot x minus 3t, then what I want to do here is I want to plot it at 3 different times, okay? So I've got 1 over x minus 3 times 1 whole squared. I've got 1 over x times 3 minus x times 3 times 2. 1 divided by x minus 3 times 2 whole squared. And then same thing with 3. So basically these are my times. T equal to 1 t equal to 2, and t equal to 3. And you can see down here what those plots are going to look like. Does that make sense? How does that line up with what I just put up on this picture right here? That's my function, right? Now, I'm not going to plot a function of x and t. I'm just going to plot what the function looks like at various values of t. So we're plotting it at t equal to 1, t equal to 2, t equal to 3. And if we do that, before I do it, does this make sense? Are you all on board with what I'm talking about here? Anyone have any questions? If we do that, we get a traveling wave. At t equal to 1, the wave is right here, the blue line. At t equal to 2, the wave has traveled, we call it the wave pulse, has traveled from there to there. At first it's centered on x equal to 3, now it's centered on x equal to 6. And then at t equal to 3, it's traveled to here. And you can imagine creating an animation by which you have this wave that's basically just traveling to the right, like this. Does that make sense? Are you all confused? So the shape of the pulse is given by this expression, and then we just shift it. And y'all know if you shift an equation by varying amounts here, it'll just basically move to the right? Does that all make sense? Is that too much? We can change the function too. So instead of using this inverse function here, you would. Should we do that so it's more clear what we're doing with that differential equation? So Mr. Mary said you would take the double derivative for the partial differential equation. Sure. Let's see. Do we want to use this one? There's a lot easier versions of this we can do. We can do this one. That's fine. This is not that hard. So our function y of x and t is equal to basically x minus vt to the negative 2, right? If I take del y del x of this, I'm going to get negative 2 and then add 1 to the power, right? Does that look right? Is that the right derivative? Doing the partial of y with respect to x. Bring the 2 down in front. Take the derivative of the inside. Multiply by the derivative of the inside function, which is x, so just 1. Okay? And then this says we have to take the second derivative, right? Take the second derivative. So we take the second derivative of y with respect to x. And now what we're going to get is we bring this one down in front. Oh, no. This is special because this is just... Wait a minute. The integral of 1 over x is natural log. This should have been to the negative 3, right? Yeah, okay. I knew that was wrong. I was like, I'm thinking about integrals. This should have been negative 3. Yeah, okay. Take the derivative again. So negative 3 times negative 2 is positive 6. And then we have x minus vt to the negative 4 now, right? Okay, right alongside this, let's do del y del t. The right-hand side says to take the second derivative. So for this one, we're going to get same thing. You bring the negative 2 down in front. You have x minus vt. The power becomes negative 3. But now we need to multiply by the derivative of the inside, which if we're doing the partial with respect to t, that's going to be negative v, right? So we need to multiply this whole thing times negative v. So we're actually going to get 2v multiplied by x minus vt to the negative 3. Okay, does that look right? Before I continue. Other people agree. Anybody else? I'll just wait to make sure you're all caught up. Anyone else want to confirm that's what the partial of y with respect to t is? It's Mr. Meower is the only one left. Did everybody else already go? Thanks. Okay. All right. Now we want to take the second derivative of this function here. So the derivative of this one is going to be negative 3 times 2. So we're going to get negative 6. Subtract 1 from the power. We again have to multiply by the derivative of the inside, which is negative v. So that's going to give us a negative v times a negative v, so we'll get a v squared right there. Hopefully you can see it now, because what we have to compare is basically, according to our wave equation, this needs to be equal to this multiplied by 1 over v squared, and it is, right? Can you see how it satisfies that equation right there? If I divide this one on the right by v squared, I get the one on the left, right? That means it satisfies the equation. Now, you should be able to prove in general that any function will work that way. Literally any function. As long as it's a function of x minus vt, it will work. Yeah. In addition, it helps, I think, to see visually that this does in fact look like a wave. Because after all, you get a wave like this. And just to show you that it works with any function, I didn't just pick a random function that I knew would work. Let's change this to the following function. Let's use the exponential. So I don't know how this works with this one. If we do e to the... I'm going to make it to the negative 2. No. I want to do it like this. Let's do that. So I'm going to change my function. Instead of being 1 over that thing, I'm going to make it like this. And this should also produce a similar type of thing. In fact, this might even look better because I think it's going to be a Gaussian. I think that all looks right. Yeah, so we've got e to the negative x minus 3 times 1, x minus 3 times 2, and x minus 3 times 3, and boom, look. Exact same thing. Traveling wave, except now it's like, it looks more like a pulse, right? It looks more like a pulse. And the size of the pulse is the same at every point. And it literally just, the pulse just travels along, just like a pulse on a string would, just like a pulse on a hose or whatever. There you go. That's a traveling wave, right? Okay, so that function would also satisfy the wave equation. It would have been a little easier to do too, probably. Yeah, maybe, I don't know. All right, so there we go. That's the wave equation. So our goal is to prove that the electric and magnetic fields of Maxwell's equations can produce this exact same equation here. And if they can, and if the velocity that shows up here is the speed of light, we'll kind of have done our job. And that's our goal with what we're going to do now. Okay. Before we continue and get to actually proving this, I want to write down some of the properties of electromagnetic waves that we know. So I guess I should write these down because I think if I type, it's just going to go way too fast. So 10, there it is. Okay, so first of all, it's a transverse wave. So EM waves are transverse. This means they're like water waves or waves on strings, in the sense that the propagation of the wave is perpendicular to the magnitude of the fields. So that's to say that the electric and the magnetic fields are perpendicular to the direction of propagation. Or the velocity. And the direction of propagation is given by doing E cross B. There is a fixed ratio between E and B. And that ratio is that the electric field is equal to the speed of light times the magnetic field. The wave travels in a vacuum with a constant speed. We call that speed c. This number is, as far as we know, this is a constant speed for all observers. Anyone observing a light wave and measuring its speed would say that it was traveling at that same speed as long as they measure the speed in a vacuum. The speed of light changes when you get into different materials. For example, the speed of light as it travels through glass is about half. I think it's half the speed in glass. It's C over N, and N for glass is 1.5, right? It's 2/3. Sorry, in glass, it's 2/3 the speed of light. Yeah. And then in water, it's like 3/4 the speed of light or something like that. But in vacuum, when we say that, we mean like in the vacuum space, it travels with a constant speed. Unlike mechanical waves, there's no medium needed. Or what I would say is the medium is basically the electric field and the magnetic field. That's what I would say. But it's not exactly a medium. Okay. I think we can get into the derivation now. I'll say some of these other things as we go through them. They also bring up polarization. We can talk about polarization in a little bit, but I'll mention it as we kind of draw pictures here. All right, so we're going to imagine also that these electric and magnetic fields are going to be constant over a single plane, but they're going to continuously vary in the x directions. That's going to kind of be so our plane waves will have the y component of the electric field and the z component of the magnetic field constant over one plane. I.e. the yz plane, but will vary as you move along the x direction. We'll say from plane to plane. And I'll draw a picture of that now. I don't know if I want to draw a picture. This is really difficult for me because I can draw a picture that would look pretty good. It's going to take a while though, so I'm just going to use their picture. I can't... I know that when I just copy-paste a picture like this, that it deprives you of the time during which I would be drawing it. And while I'm drawing it, sometimes it can help you to see what's going on. But here, let's make this even bigger. We don't need the whole thing on the page at the same time. Here we go. This is what our plane waves are going to look like, okay? Well, let me say what I meant when I wrote this purple thing here. So our plane waves are going to be such that the electric field is only going to oscillate in the y direction, and the magnetic field is only going to oscillate in the z direction. The electric field could be positive or negative, meaning it could point below the axis, below the x-axis. And when I say that our plane waves will have EY and BZ constant over one plane, what I mean is that on like this front plane right here, our electric field, which points up here, and our electric field, which points up here, these are going to be the same. These electric fields are the same, and the magnetic fields are the same, okay? But in planes that are adjacent to these, like the one that's behind it or the one that would come next, the electric field is going to be different. Okay, so the electric field on the plane to the left is different from the electric field on the plane to the right. The one thing that they have in common is that the electric field is only going to oscillate along the y direction, and the magnetic field will only oscillate along the z direction like this. Okay. They vary from plane to plane. That just means that they're varying in the x direction here. The way that I would really think about this personally, imagine that there's like an oscillating sine wave that represents the height of the electric field, and it's oscillating up and down like this, right? So if I was to just look at the y-x direction here, then what I would see is that electric field vector that's on my picture there, it would basically have a profile that would look something like this. At one point in time, the electric field is like this, and then it gets bigger, and then it starts to get a little smaller, and then it becomes negative, and then it becomes positive, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it becomes positive, and then it becomes negative, and then it gets smaller and smaller, and then it repeats the process, okay? So that on adjacent fronts, you'd be thinking that there's like a you could kind of connect the tips of the electric field vectors to produce a wave like that. That's how I think about what's happening here. But it does not have to be a sine wave. It's just the sine wave is probably the easiest thing, at least for me personally, to visualize. It could be something like the wave that we just discussed a second ago here. It could be a wave that's a pulse, just like this. It does not have to be a sine wave. Okay. Does that make sense? This, and each one of these is a plane wavefront, okay? Like we said before the break, the idea is it's a big plane, it's a wavefront that carries all the energy of the wave, and it's just moving through space. Okay. What we're going to do is we're going to look at two. I'm going to stop for a second. Does anyone have any questions? Does the picture make sense? Don't worry about the GFHE thing here. We'll talk about that in a second. Okay. So, this is what we need to do. We need to look, for example, at one of Maxwell's equations, okay? The first one that we're going to look at is this one. Integral of E dot dl. This is Faraday's law, right? Faraday's law, it says right here. We're going to apply this to what's happening here. Faraday's law says that if I take integral E dot dl, that it's equal to negative d phi b dt. We'll start with the left-hand side first. And in order to do this, we need the other half of this picture here. So let's scroll down a little bit. So what we're going to do is we're going to just look at the xy plane. So here's my xy plane. X direction here, y direction here. We're looking at two plane wavefronts that are separated by a distance that we're going to call delta x. So it's the distance between the wavefronts, and that shows up on the secondary picture right here. We're going to do a path integral, and we're going to go around our path integral in this direction here. We're going to go this way, and then this way, and then this way, and then this way. We're going to do a closed integral of E dot dl around this loop right here. Okay. If we do that, then what we're going to get... Oh, and the size of the loop that we're going to do has a height a. So we're doing a loop around this rectangle right here. Okay. And then the area vector is kind of coming out of the board. Actually, the direction of the area vector determines the direction of the loop as well. If you do the right-hand rule, point your thumb out of the page. Okay, so what do we get when we do this? So, on the left-hand side right here, we have EY. These EYs are different from each other. So what I would like to do is I'd like to call this one EY prime. Not a derivative, but it's just EY at a different location, okay? On my picture right here, what we're going to do is we're going to say start from point G and go to H, and then E, and then F, and then back to G again. Starting from point G, if my path is in this direction, so this is like my DL, these are like my DL vectors, these little things right here, then on the left-hand side of this, what I'm going to get is EY times the length of this, which is A, but there's going to be a negative sign on it. And what I'm going to do is I'm going to write this as EY of X and T multiplied by A. We keep going from H to E. I want to write above this. This is from G to H. Next, we're going to do H to E. If I go from H to E along this line right here, I said from the beginning that the electric field was only going to point in the y direction. If it only points in the y direction, when I do electric field dot product with a vector that points to the right, they're perpendicular to each other, so we're going to get 0. From E to F, the direction of the path right, the path, dl, is the same as the direction of the electric field. So here we're going to get positive Ey prime. But I'm going to write this in a different way. Instead of just calling it Ey prime, I'm going to say it's the value of the electric field, the y component, at a position of x plus delta x, but evaluated at the exact same time, t. It's two consecutive wavefronts, and we're doing the integral at the values that they have at the same time, t in this case. Plus, we need to go from f to g. And, oh, whoops, I left something out here. This is times a. It's E dot dl, which basically means you're doing E times L in this case, because we're going to say that Ey is constant over this region. This whole thing basically just ends up being E times L, basically. But you need to take into account the dot product. So from F to G, we're going to get 0 again, because our path is like this, but the electric field vector is perpendicular. So all in all, what we end up getting is negative Ey of x and t plus Ey of x plus delta x at the same time, and then all of that's multiplied by a. That's what we get for doing the left-hand side of our equation, E dot dl. We haven't touched the right-hand side yet. All we've done is this part. We need to do this still. Do you all follow that? Does anyone have any questions? Great. All right, we'll come back to this equation here. I don't know why I did that. We'll come back to this equation. So that's our kind of, we're stopping right there for now. Just going to box it in. We'll do the other equation as well. So now we need to do the flux. Let's use red for the flux. Now the flux is going to be really easy here. For the flux, what we're going to say is that if we assume that delta x is really small, in such a way that the magnetic field is roughly constant, we're going to say Bz is approximately constant over this region, then we can say that the flux, phi b, is just going to be equal to the value Bz multiplied by the area of this whole thing here. And the area is A times delta x. Okay? So even though we're saying that the magnitude of the magnetic field is changing from wavefront to wavefront, we're kind of just, you could think about this as taking the average magnetic field right here if you want to. If you really want to. But I'm going to write it like that. Okay? And then the right-hand side of my equation now, maybe this is kind of confusing here. Maybe I need to get rid of these. Here. It's not working. It's not erasing. Oh, there it goes. Okay. It's Bz times A times x, delta x. It's not a function like we have up here. Bz itself is a function of x and t as well. Okay. It's not a function of z, and it's not a function of y. It's only a function of x and t. But that's our flux, right? So we're kind of done, actually. Because now all we need to do is to put together our two equations. So putting those two equations together and using Faraday's law, what we're going to have is the integral of E dot dl, which is equal to all this junk. So we have, let's use for our final result here, we'll use a different color. So we'll have negative Ey that whole thing multiplied by A is going to be equal to the time derivative. And now I'm going to kind of, without explaining much, I'm going to change the derivative from a hard derivative to a partial derivative, which we kind of have to do because bz is a function of x and t, so we're really required to do that. And inside of here, we'll have the function bz, and then still a times delta x. All right, so we've applied Faraday's law. That's what Faraday's law says about our wave. And we're gonna do some things here. First of all, we're gonna cancel the a from both sides. We're gonna divide this delta x piece to the left-hand side, and I'm gonna reorganize it a little bit. So I'm gonna rearrange it so that it's the positive term is first. So what we're gonna get is ey of x plus delta x minus ey of x divided by delta x ends up being equal to negative del t of bz. And then we got to think about the left-hand side here, and we don't have much time. I kind of want to get through this relatively quickly here, but I want to make sure you understand, especially the first one of these. We'll just repeat it in a second, but what is that thing on the left-hand side then? Does that look familiar to y'all? Right. So what I should say is now let's take the limit as delta x approaches 0. I'm sorry, I left that off. Yeah, what does the limit do exactly? What is that? What is that thing on the left-hand side? If you take the limit as delta x approaches 0, what does it become? It doesn't become infinity. No. Yeah, think back to either pre-calculus or calculus 1, the very, 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 very beginning when you were talking about derivatives. It doesn't have a simple answer. It's not like the answer's 2 or pi or something like that. No, it's not like that. It's going to be this is something that you learned in mathematics. See, if you think about what it's saying, I think Ty knows the answer. He's just holding back. It's the derivative. This is the definition of the derivative. It's the derivative of this function, basically, right? More specifically, because of the fact that the time is held constant, what kind of a derivative is it? It's a partial derivative, right? It's a partial derivative. The thing that's written on the left-hand side right here, we have a much simpler way of writing it, and we write it like this. We say del ey del x. That's what it is. That's the partial of y with respect to x. And if you don't know why, it's because you're saying take the value of a function, right, at some coordinate, x plus delta x, subtract from that the value of the function at another coordinate, and then divide by the distance between those coordinates. That is quite literally the first definition of the derivative that you guys probably learn about in your... And, yeah. So this apparently, del ey del x is equal to del bz del t. Okay, we'll come back to that. But that's... This is Faraday's law now, just written in a much simpler form. Okay? So just think about it. We started with our normal Faraday's law, right? That we've been using for quite a while. And boom, that's what we got. Okay, so the next thing to do, we used Faraday's law. The next thing to do is to use the Ampere Maxwell Law. Okay? For that one, I believe I have another picture over here. Okay, so this one I'll go through a little bit more quickly because we'll know all the answers already. So now we're going to apply Ampere's law. Squish that down a little bit. I think it still looks okay though. Exact same picture as before. We've got two plane waves separated by a distance delta x. Electric fields and magnetic fields are drawn here. Now what we're going to need to do is we need to evaluate another thing. We need to do integral of b dot dl. Okay, similar to what we did before, except for it's the electric field. And this one should be equal to, according to Maxwell, the, the time derivative of the electric flux. No negative sign on this one. So we need to evaluate b dot dl. That's the first thing that we'll do. So integral of b dot dl Here's our loop. Now what we have to do for this one's a little harder to visualize. We're going to look at it from top down. So your eyeball would be up here, and we're going to imagine flipping it so that the z-axis points downwards like that, and the x-axis points to the right. Okay? That's what we're doing. And then this is going to be our path, FG. You can see FG shows up here. H to E is at the bottom. So there we go. We want to go around this path. Again, the direction that we travel around the path is given by our area vector here. Area vector pointing up means that the path that we're going to go through here is going to point like this, like this, like this, and then like this. The magnetic field is going to be that. So let's start from G. Okay. Starting from point G, integral B dot dl is going to be equal to, we've got BZ times A. From H to E, you get 0. I'm not going to write that down, so plus 0. But then when you go along the right-hand side from E to F, so this is G to H. When we go from E to F, we're going to get minus, because BZ and DL are in opposite directions. This is DL. DL is up and BZ is down, so the angle between the two of them is 180 degrees, or pi. So when you do the dot product, you get a negative sign. So we're going to have BZ, but now this BZ is evaluated at a point X plus delta X. So same thing as before. A lot of similarities here, right? And then again, that's multiplied by A. And there we go. That's the left-hand side. Right-hand side, once again, we're going to say, assume that delta X is small enough that we can take the average value here, and that we can define our electric flux to simply be equal to the value of the electric field in that regime, which was EY, multiplied by the area, which is A times delta X. When you do it like this, I hope that you're able to see just how completely symmetrical these last two equations are, right? We literally get the exact same type of thing here in both cases. It's pretty amazing. All right, so that's phi, but we need to combine them together with that equation, right? So let's do that. So our equation says integral B dot BL, that's the left-hand side here, so we write BZ of X and T minus BZ of X plus delta X. Both of these are multiplied by A, and they should be equal to the derivative of the flux, except it's multiplied by mu naught epsilon naught, so we got to leave that in here. So mu naught epsilon naught there. And then the partial, we'll just immediately write down that it's partial derivative now of EY. And that's also multiplied by A times delta X, except what we'll do is we'll cancel out those A's. We'll move the delta X to the left-hand side. We'll rearrange it just a little bit. So what we're going to do is we're going to write it like this. We're going to write BZ of X plus delta X, comma T, minus BZ of X and T, except now we're going to just basically pull a negative sign out of this whole thing. We're going to divide by delta X and say that's equal to mu naught epsilon naught times the partial derivative of EY with respect to time. And then we take the limit as delta X goes to 0. The left-hand side now becomes the derivative again, but now it's the partial derivative of BZ. So we have del BZ, del X. On the left-hand side, a negative sign, and it's equal to mu naught epsilon naught del EY, del T. Okay, we're almost there. So I'll stop for a second and ask if you have any questions. We have that equation, and then we have this equation. I'll copy it down here. Whoops, I didn't mean to cut it. Copy. Paste. Those are our two equations, right? Does anyone have any questions? The limit here? I mean, I'm always allowed to perform this operation. You know, this is an operation that we're performing on the left-hand side, but it doesn't affect the right-hand side because there's no delta x's over here. So it's okay to say, apply this operate. So, I mean, you can do things like, I can take anytime I have an equation, as long as I do the same thing to the left-hand side as I do to the right-hand side, it doesn't change the equation, right? So I could, for example, square both sides, I could square root both sides, or I could take the derivative of both sides, or I could take the limit of both sides. Or what I could have also done, by the way, is I could have just avoided doing the stuff with the delta x stuff, and I could have, what I actually could have done is, instead of writing del bz here, what I could have done is I actually could have written this as the same I'll leave that for another time. We're going to talk about that later. But there's another way I could have done this that would have completely avoided ever calling this delta x. I could have called it dx, and I could have avoided ever taking the limit. So, yeah. No, we're going to talk about what I just said at another lecture. I'm not, don't worry about it. I'm just saying there's more than one way to do this where I wouldn't have had to do the limit. But at the end of the day, there's nothing wrong with doing this. Right? And it's not random. I mean, it's because you look at this expression and you know that that's the definition of what a derivative is, basically, as long as you take the limit. So, if physicists would say you don't even need to take the limit, they would just say that's what a derivative is. But different story. Okay, so we have these two equations here, right? And what we really want to do is we want to make them somehow look something like each other, so that we want to merge these two equations together in some way. But if you look at the way that they're formed right now, while there's a lot of things that are similar, they're not exactly the same, right? You'll notice that where the electric field shows up in the equation on the left, the green equation, it's a time derivative, right? But when you look at the same thing over here, it's an x derivative. Okay, so they're not exactly the same, right? And same thing is true with the magnetic field derivative. This is the spatial derivative with respect to x, and over here it's a time derivative, right? But they both have the same minus sign, so that's promising. But then you've also got this thing here. So why is that only showing up in one place? Well, when we combine them together, we'll get everything that we need, but we need to do one other thing. What we're going to do now is we're going to, on the equation on the right, we're going to take the partial derivative with respect to x of the whole thing, okay? And on the equation on the left, we're going to take the partial derivative with respect to time of the whole thing, okay? So, the left-hand equation, what we'll get, if I take the partial derivative with respect to time, in the numerator what I'll have is negative second derivative of bz, but it's a mixed partial where we're doing del t del x. On the right-hand side, though, because this is already a derivative with respect to time, we'll get mu naught epsilon naught, and then we'll get del ey, but it's now going to be a second derivative with respect to time. Right, so I'm basically taking the time derivative of something that's already a time derivative, so we get the second derivative, right? For this one, what we'll get on the left-hand side is we'll get the second derivative of ey with respect to x. And on the right-hand side, what we'll get is, again, a mixed partial, because it's del x and this is del t. So you'll get the second mixed partial here. And if you haven't seen stuff like this, because you haven't taken Calculus 3, I don't know. Go read about it. It's a lot of, I mean, you can look in Stewart, and you can go read about partial derivatives. They're pretty simple. We've talked about partial derivatives before in this class, so I'm not going to do that at this time. But if you want to talk more about it during the break or after class, we can. But all this really means, you probably understand the left-hand side if you've taken any calculus. This means take the second derivative of the function ey with respect to x. This means take the second derivative of the function ey with respect to t. And after all, these functions, like ey is a function of x and t, and bz is a function of x and t. And the only reason we're even writing these components of ey and z, the y and z here, is just because our electric field only points in the y direction, right? Another way to write it would just be to, yeah, but anyway, so we get these two equations here. And now they're equal to each other, right? Now they're equal to each other because they both have, oh, I dropped a negative sign, by the way. I'll put it in a different color to make it clear that I dropped it. There is a negative sign on this one here. From right there. I just dropped the negative sign. But they're 100% equal to each other because this term and this term are equal. So that means that the equations are equal. Which means what we have now is I'm going to write it in a slightly different form. Kind of our final result here is that the second derivative with respect to with respect to x of Ey, which is a function of x and t, is now equal to mu naught times epsilon naught multiplied by the second derivative of Ey, which is again is a function of x and t, with respect to time. And this is a wave equation, because our initial wave equation, if we want to go back to it real quick here, looked like this. You take the second derivative with respect to x, it's equal to the second derivative with respect to time, but then the thing that shows up here is the velocity squared, 1 over the velocity squared on the time side. So our time side is the right-hand side, and that means that this expression right here, mu naught epsilon naught, has to be equal to the speed of the wave, or more specifically has to be equal to 1 over v squared. You rearrange this and you get that the velocity of our wave is 1 over the square root of mu naught times epsilon naught. Right? And this, as I said at the very beginning, if you calculate what it is the speed of light in a vacuum. So the other way to write this equation, which is probably the better way to write it, is and that shows that the electric field satisfies a wave equation. Right? The electric field satisfies a wave equation. And we could have done exactly the same thing if we wanted to get the magnetic field into here. So both the electric field and the magnetic field satisfy wave equations, okay? I'll write down, if you can show for yourself, I think this is probably a problem in your textbook, not a problem I would have assigned, but you can show for yourself by doing a different order in which you take those derivatives that I did above, I'll point it out, that it's also true that the magnetic field will satisfy the same wave equation. Except it's Z, isn't it? Sorry. This is BC. So both the electric field and the magnetic field satisfy the wave equation, and therefore this kind of explains why it is that the electric and magnetic field are what it is that composes light. And this was exactly what Maxwell thought when he was going through this process. Is I think he kind of knew that just knowing that this thing had this relationship going in, he knew as long as he was careful enough with all of the calculus that he was doing and solving this differential equation, that it had to be the case that this was going to work out. And he just needed to make sure that it's very much a situation where he kind of knew the answer that he was going to get. He knew that it had to work out this way. I mean, he had enough confidence, at least, that it had to work out this way. Because up till this point in science, apart from being able to observe light, and apart from knowing some of the properties of light, like reflection, refraction, interference, and all these things you'll learn about in Physics 1D, no one had any idea what light was. No one had even an inkling of an idea of what light was. There were ideas, it's this fluctuation of the ether and all these kind of things, but no one had any idea what it was, because if you ask the question, what is light, they would say, well, it's a wave. Or they'd say it's this thing, that oscillates, and yeah. But they didn't know what it was made of, right? And Maxwell figured out that it's basically some kind of a disturbance of the electromagnetic field, which is really groundbreaking. It's like utterly amazing that, if you think about what happened in the 18th century, 19th century, I should say, sorry. There's just this huge revolution that occurred in physics, really, that, so this is kind of how it went. So 1820, really big year. Two things happened in 1820 that are really important, okay? In 1820, Ørsted basically unifies electricity and magnetism when he observes that a current-carrying wire can deflect a magnetic needle. That unification really, I think, belongs to people like Henry and Faraday, though, because they truly wrote out the kind of mathematics and performed all the experiments needed to prove that it was true. But it's nonetheless, it's really Ørsted that gets credit for it. And it's kind of further explained in the 1840s by Faraday and Maxwell, right? But the same year, not exactly the same year, but within 3 years of this occurring with Ørsted, is when Young and Fresnel perform what's called the interference experiment. This is the experiment that pretty much, just to give you the lowdown on this experiment verified that light was a wave. This was the light has to be a wave experiment. They were like, oh, light's a wave. Check that off. We know now light's a wave. The Young interference experiment, right? But nonetheless, these two ideas, electricity and magnetism and light, were two completely separate concepts, right? And then 45-ish years later, in 1865, it's 1860s, I don't know if the date's right, Maxwell did what we just saw. Maxwell basically shows that light's an electromagnetic wave. Very similar to what we just did here, although he did it with like vector calculus. It's a little more complicated, but so effectively, Ørsted unified electricity and magnetism, and 45 years later, Maxwell unified optics, electricity, and magnetism all into one thing, and it's 40 years. I mean, that's nothing. And 10 years after that, 1888, Hertz proved Maxwell was right by actually producing these waves. And then just a little bit after that, we're talking about like Planck discovers the idea of like quantum of energy, and then Einstein describes the photoelectric effect, and then quantum mechanics comes out. You know, I mean, it's just this rapid fire, like very, very fast paced development of science that occurred during the 19th century. And by the time, by like 1940 or something, through the 1960s, about a century after Maxwell, we understood how quantum mechanics was connected to electricity, which is obviously connected to magnetism, which is connected to light. And all of that stuff was just kind of like nicely bundled up. It's really, I mean, I think it's really impressive how quickly physics developed, because it's one of the youngest sciences. I don't know if you guys know that, but it's definitely one of the youngest sciences in terms of our understandings of it, right? Think about like the time of Newton. So like Aristotle talked about physics, but he didn't really understand physics, right? Modern physics, the kind of like, or classical physics, really starts with people like Newton, right? Being able to describe the motion of the heavens, right? And chemistry and biology had existed much long before this. But physics kind of solved itself in a way very quickly. By the beginning of the 20th century, they thought that they had solved all of physics, basically, other than a few minor things. They thought that what Maxwell had done had basically finished up physics. Things were like kind of nice and tidied up. And all of that occurred over a few hundred years or something like that. Anyway, so this is our evidence that light is an electromagnetic wave, and it travels with a constant velocity in the vacuum. It doesn't seem to need a medium. It seems to propagate along fluctuations in the electric and magnetic fields, and it satisfies a wave equation, so it's a wave, right? And all those things were good because, again, Young's interference experiment had shown that light must be a wave. This is another explanation of light as a wave, right? It's a waving electromagnetic phenomenon. And then Hertz proved that it was real. So I think that's all pretty fascinating. The history of physics is very interesting. Well, does anyone have any questions? Okay, if not, we'll take another break. And then we'll start looking at some applications of these ideas.